Welcome back to Differential Calculus. In this video, I want to talk about relative extrema. You've heard of the idea of relative extrema in a previous math class, I'm sure. The real idea here is I want to show you how we can use calculus to help us identify relative extrema. All right, so we'll start off with the definition. For some function f, real-valued function which is continuous on an interval, and the only thing we care about the interval is that there is a point C in the interval. We say that C is a relative maximum of f if and only if there is a value delta greater than 0 such that f of C is greater than f of x for every x such that the absolute value of x minus c is less than delta. We have a similar definition for a relative minimum, where the only change is that we want f of c to be less than f of x. All right. If that definition is clear as mud to you, then you're probably in the right place. Let's take a look at a graph and see if we can make this make a lot more sense. All right, so here I am in Desmos. I have a function graphed. You can see the particular function above my head, but it doesn't really matter. All that matters is that it is a function. And we have a point right here where the graph turns around. That point is a relative maximum of the function. If I zoom in really close on just that point, what we see is that in this neighborhood of the point, if I pick anywhere else, any distance away from the point, I always get a value of the function less than the value of the function I get at my point. All right, that's what the definition of an absolute maximum is trying to talk about. If I zoom back out here, I have a second point down here, which is exactly the opposite picture. If I zoom in on this point far enough, everywhere I look, the value of the function is bigger than the value of the function at that point down there, which is why we call that a relative minimum. All right, you've probably thought about these ideas in terms of a graph in the past, and I really haven't changed anything besides giving us a formal definition of what it means. But having that formal definition will help us in that it will allow us to start looking at how to identify where these extreme values come from. All right, so going back to my notes here, collectively, these points are relative extrema. All right, so any relative maximum is a relative extrema. Any relative minimum is also a relative extrema. It's a collective term so that we don't have to think about these things as separate ideas. Right. At a relative maximum, we know that there is some interval on which the function has to be less than the relative maximum to the left and greater than the relative maximum to the right. We also know that the function has to be continuous. Right? The only way for those things to happen is if the function is increasing over here and decreasing over there. This is, again, one of those things that most students look at and say, well, obviously, and it isn't that challenging of a conclusion to reach, but it is one that we have to state, so here I am stating it. That takes us to the heart of it, though. If a function is increasing, then its derivative has to be positive. If a function is decreasing, then its derivative has to be negative. And so, an interesting way to look for a relative maximum is look for a place where the derivative goes from positive to negative. And there are only two ways that a expression can go from positive to negative, or from negative to positive for that matter. It could be that the derivative at the point we care about happens to be equal to 0. Or it could be that the derivative of the relative extrema is undefined. Collectively, these are known as the critical values. I've drawn this for a relative maximum, but a relative minimum just flips the story upside down. In order to go for a relative minimum, the function has to change from decreasing to increasing, which just as well has to fall into one of those two settings. And I'm going to draw that anyway just to show you that if I have a function that looks like this, that point is a relative minimum, and because it is a cusp, it is a point where the derivative is undefined. There's a weird corner that happens there. All right, so there is an example of equals 0, gives us this nice smooth arc where we have a horizontal tangent line with a slope of 0. We also have a cusp here, which has a vertical tangent line with an undefined slope. The critical points have to occur when one of those things happens. But we have to point out that not all critical points are extrema. So before we go and start worrying about finding critical values, the first example I want to show you is f of x equals x cubed. We know what the graph of this thing looks like. Give myself a little bit of space to actually draw it. The graph of this function looks something like that. It has a horizontal tangent line at x equals 0. But I think it's pretty clear that x equals 0 is not a relative maximum because it keeps going upward in this direction, and it's also not a relative minimum because it keeps going downward in that direction. So it just falls in the middle. that is something that can happen, and it's something we have to pay attention to. But if we know where the critical values are, they greatly narrow down the possibilities of where the extrema occur and give us a finite number of places that we can stop and look. I'm going to go to the same function that we looked at in Desmos earlier to go through an example of how to find these. If I can hit the right button. There we go. So for example, the function f of x equals x cubed minus x squared minus 6x. I know from having graphed this function that there is one relative maximum and one relative minimum. I could zoom out and see that it's not going anywhere else, but we're just going to take that on faith for the moment. But we can find the relative extrema by first looking for critical values, which means we need the derivative, f prime of x. Well, the derivative of a polynomial is relatively simple. It's going to be 3x squared minus 2x minus 6. This particular function is a polynomial. Polynomials are continuous everywhere, so we don't have to worry about undefined points. But I do want to remind you that looking for undefined points of your derivative is part of finding critical values. We just don't have to write anything in this case because we have a polynomial. All right. The other thing that we are looking at is when is f prime of x equal to 0? Well, that means that 3x squared minus 2x minus 6 is equal to 0. And, well, we could, in theory, factor this. I don't see how it factors. So I'm going to jump right to the quadratic formula. X equals the negative of b, that's going to be positive 2, plus or minus the square root of b, negative 2 squared is positive 4, minus 4 times a, which is 3, times c, which is negative 6, all over 2 times a, which is still 3. All right. 4 times 3 is 12. 12 times 6 is 72. 72 plus 4 is 76. And let's see, I guess we can reduce. 76 divided by 4 is 19. And then reduce the fraction to get that x is 1 plus or minus the square root of 19 over 3. All right, that's my exact value. That's what I've called in the past an answer only a mathematician can love. We can go ahead and punch that into a calculator. 1 plus the square root of 19 divided by 3 is 1.786 dot dot dot, and 1 minus the square root of 19 divided by 3 is negative 1.120, or thereabouts. For my purposes, I am right in front of what I want to be gesturing at. For my purposes, I want to see that kind of a solution. I want to see the exact values. For the purposes of graphing, approximate values might be more useful. The last thing I want to mention here is going back into Desmos. I showed this briefly, but let me show you again. Desmos is really good at identifying where relative extrema occur. And they make it clickable. So you can just click on the point and it will tell you, oh, that's negative 1.12. That's one of the points we found. It's positive 1.786. That's exactly what I wrote down for the other point. So that's an interesting question in and of itself. Computer software can do this now. When I was a student taking calculus, which was not all that long ago, computer software did not exist that could do this, or it existed, but it wasn't reliable. In today's software, you don't even have to tell it there's Extrema there. You just plug in the graph and it recognizes the Extrema for you and puts a big sign on it that says, hey, here's an extreme value. So what do you want to do with it? So that naturally leads to a couple of questions on what are we doing? Why are we going through and taking the time to learn this? As a math teacher, I'm supposed to tell you that the answer is that this is great practice for using derivatives, using the ideas of derivatives and bringing all of these things together in an application. I don't know about you, but I don't find that a particularly satisfying answer. Excuse me. If I don't find it particularly satisfying, why should I expect you to? Excuse me, sorry about that. If I don't find that answer particularly satisfying, why should I expect you to? For me, as a person who is interested in researching about mathematics and about advancements in the tools that we use to study mathematics, I find that this is interesting from the computer science perspective. Somebody had to write the program that was able to understand how to identify relative extrema. And the person who did that had a very good understanding of this kind of, I didn't mean to get myself out of there, this kind of analysis. So in order to write even better software, we need computer scientists who know how the software works. To me, that's reason enough in itself to study these sorts of things. There is one more situation to think about, and that's the one of the natural sciences and data collection. Very often in the world, very often in the ways that physicists and engineers and chemists and biologists and finance specialists, economists use calculus is from a completely backwards direction of how we do in class. Usually, there is no pretty expression for the function. Usually, it is a matter of going out and collecting the data and trying to decipher things from that. So you have data points, and you're trying to find extrema from data points, which involves writing some software to analyze, to interpolate, and to go from there. Excuse me. That is another place where having this foundation allows you to do that analysis. Having the foundation, having the understanding of how we can identify them when we're working with pretty functions will get you that one step that you can then build off of to work with the uglier functions in the future. All right. But for now, let's wrap up with one for you to try. So here's another cubic polynomial for you. G of x is 2x cubed minus 15x squared plus 24x minus 7. I would like you to identify all critical values and then classify relative maximums and relative minima. All right, take a couple of minutes, see what you can do with that one, and I'll see you in the next video.